So for those of you who come in new here, you're jumping into day 2, which already has confused many. That was your first test. Day 2 is a euphemism for day 1, of course.
And we really aren't crazy. It's just that we started out teaching 5 days, but it just became too much to teach 5 days in a row, 8:30 to 5:30. So we decided to start teaching 2 at a time. But we didn't want to change the numbering because people purchase the handouts and they have certain meaning. So day 1 is day 2 is day 5A, and day 3 is day 5B. So you're not crazy if your handouts say that.
But it does have a significance because it tells you that there's something that goes before this day, right? That is, there are certain desired prerequisites, not totally necessary, but desired. The optimal way into day 2 is clearly day 1. So if you don't understand anything today, then come back in March, because then day 1 will be taught. So the sequence of courses starts over pretty much in March 2008. It will be day 1 and day 2, and probably some excerpts from a so-called day 3, which we're skipping over here today. So anyway, there is a system to the madness here, because day 2 is growth modeling, which can be seen as a multi-level model. And multi-level modeling is the key topic here during the 3 days. Tomorrow will be the traditional, conventional multi-level modeling of cross-sectional data, cross-sectional as opposed to longitudinal data. And you will see many connections between today and tomorrow in terms of the modeling features. And then on Wednesday, day 5B, day 5, which was the multi-level day, had to be split up into 2 parts because so much happened in the last year or so. And actually, day 5B is quite advanced on the research frontier, so that should be of interest to many of you who want to draw on the latest technology, get the latest high-tech publications out, and even those who are methodologically inclined and want to do method studies. Day 5B also contains some interesting upcoming features in the upcoming Mplus version 5, coming out sometime in the fall. We used to be more specific about when versions come out, but we were always wrong, so now it's sometimes in the fall. So that may be in September or in December, who knows?
What? We don't know.
So, okay, so is everybody seated and comfortable? All right. Should we perhaps start?
Yes, and just because a lot of people have come in, so we have 4 segments, and we ask that you hold your questions until the question and answer period at the end of each segment. Okay, so you can start.
So many of you have been here before and heard these things, but there are several of you who are new. So I just wanted to give a quick background for why we decided to develop the Mplus program, despite the considerable effort that goes into a software piece. We found that there were a lot of interesting statistical methods that were not used commonly in practice, despite them being quite intriguing and useful on the paper, at least statistically speaking. So biostatistical and psychometric contributions underutilized in practice. And when the methods were presented, we saw them as being technically described in very, very many different journals. If you want to try to keep up on methodology development, and I do, tie, I have to look at about 20 different journals, sociology, marketing research, statistics, psychometrics. There are a lot of good methods, folks, in many different areas, which makes it hard to keep up with what's happening. And when software is presented, it's often in terms of very limited software that works with this person's research paper, often written in software that's not easily used, like little pieces of R software, for instance. So we want to integrate all of these methods, and as many as we could that are relevant for analysts, modelers, in one framework, trying to make it easy to use, while at the same time being uniquely powerful with very, very many general modeling capabilities. And we started that not even 10 years ago, so it's a very new program. And the current version is 4.2 actually, which 4.2 is really a version 5 because so much happened between version 4 and 4.2. Lots of mixture modeling applications, extensions came into 4.2. Came in so fast that we didn't even have time to put it in the user's guide. So the user's guide that you have, and we have 2 up here, does not contain all of the features in 4.2. There's actually a user's guide addendum that sits on the website of Mplus, and the whole user's guide sits at the website. So the team is Linda and I, and Thuy Nguyen is a programmer who does the front piece and back piece of it, and the middle piece is done by Timur Arohov, a statistical person who has a math PhD from Caltech and is very clever with algorithms and all kinds of extensions of models. So he and I work together quite a lot, and Linda and Thuy work together quite a lot, and then we have Michelle Kahn who runs the Mplus office. So it's a small team which has its interesting possibilities of being able to move forward quite quickly on new methods development, sometimes more quickly than we feel we can keep up with ourselves. So the unifying theme of this is latent variables. So the reason one can do so many things, many types of modeling activities that seem so different is because there is a unifying theme of latent variables behind it. So you have the statistical concepts captured by latent variables on the left, and the models that use those concepts on the right. And typically, we talk about continuous latent variables in latent variable modeling in the form of taking into account measurement errors and focusing on more fundamental constructs, so-called factors. But we know that continuous latent variables come into play all over statistics, even though it has different names, like random effects that we're going to talk about a lot today and actually the whole week. Frailties and liabilities is talked about in survival analysis and in genetic analysis. And variations on components of variation on different levels, students, classroom, school, are latent variables as well, giving rise to variance components on different levels. Missing data on a continuous variable is, of course, a continuous latent variable. We have focused in Mplus on integrating such models with categorical latent variable modeling, so-called latent class modeling. And we're going to talk about that a little bit on tomorrow afternoon, growth mixture modeling. First, we're going to talk about latent class analysis a little bit, particularly focusing then on 2-level latent class analysis, and then longitudinal latent class analysis. So that's focusing on clusters of individuals, trying to group individuals into different classes that are different. In statistics, that's called finite mixture modeling. And if you have missing data on a categorical variable, well, then you have a categorical latent variable. So then you see all these familiar terms of factor analysis, structural equation models, growth curve models, multi-level models that use these continuous latent variables and that use these categorical latent variables over here. We're not going to have time to talk about survival models or missing data models this time. If you come with us in 3 weeks to Florence, Italy, we'll talk about this a little bit. It's just a hop, skip away. By the way, there's another upcoming multi-level session in Europe. There's some from Europe here, from the Netherlands too. I forgot to mention Netherlands, right? Who's from the Netherlands here? One person. All right. And from South Korea too, but the United States, I believe. All right. There's going to be a one-day meeting in London on December 5th. Multilevel modeling arranged by the Royal Statistical Society. And on the 4th, we're going to give a one-day training session on that topic in London, if you're in that neighborhood. Now, here's what the modeling framework looks like. We're going to take a look at these kinds of model diagrams quite a lot and mainly present modeling ideas in terms of figures. Wow, it moves. It hasn't moved in years. I like that. So just for those who are totally new, the boxes are observed variables, the circles are latent variables. F stands for factors, which is what we tend to use in the user's guide to denote continuous latent variables. C stands for categorical latent variables. Y is for continuous dependent variables, or at least dependent variables that have a variance parameter connected with it. U, on the other hand, is a dependent variable of the other kind, namely categorical or Poisson count variables that don't have specific variance parameters connected with them. You have all of this described in the user's guide, but it's summarized here. And on the right screen there, you can see that there are different modeling frameworks zooming around, Framework A and Framework B. And it's interesting to see that, well, let me go back and also show this first. Not only do we have these kinds of observed variable types and these different kinds of latent variable types, but we also make a distinction between single-level and multi-level data. So the simplest case is that we have two-level data. We have within cluster variation and between cluster variation. So this could be students within school. This could be across school or between school variation. We're going to talk about that quite a lot. The interesting thing here then is, if you go to, well, let's see, that this framework covers so many different kinds of situations that we have here then the explanation for the days, the notation of the days. We have day 2 here, growth analysis day. And it's classified by focusing on continuous observed variables. We're going to talk very little about categorical observed variables today. And we're going to focus on continuous observed and continuous latent variables. And making the distinction between cross-sectional and longitudinal data, we then see that in the cross-sectional continuous case, we have standard linear regression and path analysis. We have exploratory factor analysis, confirmatory factor analysis, structural equation modeling. All of this then will be covered in the so-called day 1, which will happen again in March 2008. So we're over here in growth analysis. Now, in these two areas, day 1 and day 2, they belong in ellipse A over here, just to familiarize yourself with this kind of notation. Why do I say that? Well, we typically have continuous observed variables Y and continuous latent variables F. Now, typically here, EFA, CFA, and SEM work with continuous latent variables, right? But so does growth analysis, as we will see. That's a unifying theme here between these 2 days. Growth analysis works with so-called random effects, and they are continuous latent variables. So they sit right there. So ellipse A, that modeling framework, covers both of these 2 days. Day 3 and day 4, which you're not going to be part of here this time, is when you bring in categorical variables, particularly categorical latent variables. So that happens down in ellipse B here. We're going to bring in categorical latent variables in a bold way, but we're going to do that in a multi-level setting right away, because last time we were here and taught, which was in March, we talked exclusively about day 3 and day 4. So this is the follow-up to that day 3 and day 4 teaching. So it's assumed that you have the background for that as we go into those topics. So that's saying that what we're talking about here is day 5, these topics, continuous latent, categorical latent, cross-sectional, and longitudinal, all of that is day 5, which then grew to become day 5A and B. 5A on tomorrow and 5B on Wednesday. And those topics then sit in the full Mplus box here, namely both continuous and latent variables, either only continuous or only categorical or both at the same time, and multi-level with that extra level hierarchical data feature that we saw in the earlier pictures. So that's a quick overview just to see where you are in this. So these 5 days, each day could probably be expanded to 2 days, so we could go here for 2 weeks, 10 days probably. But we don't want to do that. So that was a quick introduction. We don't want to take too much time for introductions, says Linda, who's the taskmaster here, and instead get into the guts of things. So let's see if we can do that. So here's a data set that has given us a lot of, is it pleasure or headache? Pleasure, yeah. Longitudinal study of American youth. And that is a data set that we're going to use throughout the 3 days. It is actually not only longitudinal, but also multi-level. It is students within schools measured longitudinally. And there are many data sets of that kind, not only in education, which this comes from, but also in public health. So we're going to take a special interest in that type of data structure. And individuals are measured in grades 7, 8, 9, 10, 11, 12 in these data. So we have approximately 60 schools with a sizable sample of students per school. And it's NSF supported, so that's math and science achievement items that are measured. Approximately 60 items per test. And we're going to take a look at the details of that test and the scores that it produces. Here's what the means look like. On the x-axis, you have the grades 7 through 12. And on the y-axis, you have a score, average score. And the score scale is of little importance, it could be 500 to 660. The scaling of it's not so important. What will be important, though, throughout is that we have the same scale at all of these different time points. Time point 1, 2, 3, 4, 5, 6 here. The individuals being followed over those time points in a longitudinal fashion. So we're looking at 2 cohorts, younger and older. So here we have younger males from grades 7 through 10. And here we have the younger females. And then somehow it seems like the males overtake the females and have a higher mean at the higher grades. Females falling down to this. The distinction between the 2 curves is the cohort difference. So question is if that's a real phenomenon and if it's significant, and what it depends on that males catch up with the females. And also, the question is if this happens for any one individual or if this is just a phenomenon on the average. Is this a typical curve for any one individual? So what we really want to do probably is go away from mean curves to individual curves. So here we have individual curves over the same time span, grades 7 through 10. And the y-axis scale is a little bit compressed here compared to on the left. But nevertheless, we can see then for 1, 2, 3, 4, 5, 6 individuals, their development in math achievement across time. So this individual starts relatively low here in grade 7 and doesn't grow very much in math achievement up to grade 10. Much healthier growth for this individual starting high. So we see that there is variation in the starting point here in grade 7. We're going to call that, very often we're going to call that initial status. And there's also a difference in the growth rate across time. The growth rate across time is different. It seems like those who start higher maybe growing at a faster rate. And the question then is also, what's the functional form of growth here? Could it be said to be linear with some deviations here? For some people, is this significant really? Or is it nonlinear, that there's an acceleration here between grades 8 and 9, which one could imagine because so much of US math learning takes place in grade 8. So one should always investigate these individual curves when you start your growth modeling. True, the mean curves tell you something, but you really want to start your modeling efforts from the individual. And if you work with Mplus, then you can sit and look through the graphics feature of the program, look through your data set, just scroll through the different individuals on the screen, which could be quite an interesting thing to do, and try to figure out what is the typical development. And also, there may be subgroups of developments, certain individuals developing differently. But both substantively and statistically, it's good to start with individual development. Substantively, from the point of view of individual differences in development thinking, and statistically because any good statistical model probably should start from the individual and build up. So that's one example. And we don't have to limit ourselves to a single outcome. Here's in a case where we look at math achievement, and we might be interested in looking at in conjunction with math attitudes. And for some reason, it looks like math achievement goes up, whereas in US school math attitudes go down. The attitudes towards the usefulness and how interesting it is to study math. But you may want to look at the interplay between two processes. It could be aggressive behavior in the classroom in conjunction with reading achievement. It could be different kinds of psychiatric problems, comorbidity, developing across time. And you want to look at the interplay between two processes. And we're going to make a distinction between processes that happen at the same time, which we will call parallel processes, concurrent processes, and processes that follow each other, sequential processes, is an interesting topic as well. Here is a data set from Nancy Day's fetal alcohol syndrome group. And it looks at head circumference of newborn up to 36 months. So you have the head circumference on the y-axis here, and it's in millimeters. And the solid curve here is the average over a group of children from mothers who drank at different amounts during their pregnancy. Mothers who drank at least 3 drinks a week during the first trimester are included in the data set. Head circumference is of interest to developmental psych people because it is correlated with cognitive development. It is supposed. So we have an average curve here which is nonlinear. We note that. And so are the individual curves. These individual curves are the broken lines. So they are, in this case, from the 8 or so children of mothers who drank the most during pregnancy. So you can ask then if this starting point in head circumference is significantly lower for those children, and if the growth rate and status at 36 months is significantly lower for those for those children of mothers who drank the most. So you would have questions about influence of a covariate, as it were, mothers drinking. And in this case, it's a time invariant covariate. That is, it's mothers drinking during pregnancy. That doesn't change as the child ages. We'll distinguish that from time varying covariates as we go further. Now, with those examples, we could try to think a little bit about how we would want to model data of this kind, pick up on the features that we want to understand better, And one useful way of looking at that is to look at 3 different approaches for modeling. Let's have some nomenclature here. N is sample size, cap T is number of time points. So, so in this case, we have 4 time points for about, 400 babies. And we can use all data points. We can say that we have 400 babies observed for 4 time points. That's 1,600 observations, right? All data points. And do a single regression. Single regression of what? Of head circumference on age. Think linear regression or nonlinear regression. Y is head circumference, X is age. You want to see how age influences head circumference, right? So you do a regression. And you have 400 times 4, 1,600 data points to do a single regression analysis. You will get an intercept and a linear slope and a quadratic slope, which may correspond to that curve. What's the problem with doing that? Why don't you just do a regression like that? Why do we have to come to Baltimore for this course in the middle of August? Well, it gives an intercept and a slope, or several slopes if you have a quadratic, one intercept and one slope for all of these individuals. So it does not account for individual differences in development over time, which is really what we want to study. We want to capture individual differences in development over time. And also, it does not account for the lack of independence of observations. We say 400 children at 4 time points. Those observations on the children across time are correlated because it's an observation on the same child. So we don't have independent observations. We have a so-called intra-class correlation across time, which is a common feature what we will talk about tomorrow. The lack of independence is a problem in this approach. Lack of independence typically hurts things like standard errors and chi-square test of model fit. Some of these things in the beginning I say very quickly, but we will come back to these themes at a slower pace here and there during the day today. Okay, second alternative. Now, we really want to take into account the individual differences of development over time. So why don't we just do a regression for each person separately? You have a child and you have 4 time points. That's 4 observations. You have Y, head circumference, and age at each of those 4 observations. Small sample, yes, but you can still estimate intercept and slope, right? You can even estimate a quadratic slope. Then you really would get individual differences. It gives an intercept and a slope estimate for each individual. Certainly accounts for individual differences, but it totally ignores that what we usually assume, that this sample is from one and the same population. It does not benefit from statistics at all in the sense that we draw a sample from a population. We don't want to have that many parameters. That doesn't simplify our reality or our data very much. So what you want to do is this. This is what we're going to talk about all day today. I'm going to put it on the other screen so everybody can see it, because I know that podium blocks part of your view, and the podium is immovable, which means it can't be moved. So this is for us foreigners. So now, what is this then? Well, we still use all n times t data points, like up here, and we still do a single regression analysis, but we do a random effect regression analysis, a random effect regression analysis. So we're going to take a look at what that means on the next slide, but for now we're going to accept that that gives an intercept and a slope estimate for each individual, just like we got up here. So it certainly accounts for individual differences in development across time. But it also accounts for similarity amongst individuals by stipulating that all individuals' random effect come from a single common population. Great. So we have the best of both worlds there. And at the same time, it models the non-independence of observations. The non-independence of observations is still there, but if you take it into account, it's fine. And we're going to take it into account in a couple of different ways during these 3 days. Unfortunately, I can't remember what they are, but the first approach is to model it, and that's what we're going to focus on quite a lot. So let's see. I think I'll speak from here for a while. So here is a critical slide. This and the next one are critical slides. That is, important ones. So on the left, you see at the top some equations. And we're not going to talk about modeling equations very much. Just basic, simple ones. Because we want to reach as broad of an audience as possible, not only those who studied a lot of statistics. But there's some formulas that you should force yourself to suffer through, those of you who don't like formulas. But ultimately, you can look at pictures and understand then what the formulas behind them are. But if you look up on the left here, if you want to formalize what we talked about, you have a continuous dependent variable, y, which is equal to something on the right-hand side. So you should think linear regression here. It's standard linear regression. Y is regressed on x. And what are the features of that kind of a regression? Well, we have a slope that multiplies x, tells how influential x is on y, and then the other thing that's not multiplying x is an intercept. So we write intercept here, slope there. If you want to prefer alpha and beta here, that's fine. You're going to see many different kinds of notations. Different books use different notations, and nobody seemed to be willing to yield to the other book. It's not notation. So I took another one. But for a reason. These thingies here that look so funny, they are so-called etas, E-T-A, the Greek letter. Eta sub 0 and eta sub 1. Eta then is a notation that borrows from Jurskog's literal development, which means a continuous factor. And since he got a prize from an award from American Psychological Association last Saturday, I think it's worthwhile to keep that notation here. So it's intercept eta sub 0, slope eta sub 1, and here we have another Greek figure, epsilon, which is an error or a residual. So standard linear regression. Where y is the outcome, and in this case, x is time, a time-related variable. Could be the age of the child, could be the grades 7 through 10 of the math achievement, something time-related. So I is always individual here in our teachings, and t is time point. J is going to be reserved for clusters, say schools. So if you look at this carefully, it looks like a funny linear regression, not only funny because I used eta and epsilon, but also funny because the intercept and the slope both have subscripts I. Subscripts I. Typically, you only have subscripts I, what varies across individual, for y, x, and epsilon, but we're going to have it for the intercept and the slope as well. That is the random effect feature. So when statisticians say random effects, it sounds like haphazard coefficients, but it's really a coefficient that varies. It's a coefficient that varies. In this case today, the coefficients are going to vary across I, individuals. Tomorrow, maybe not. Tomorrow, probably they're going to vary across J, across schools, multi-level modeling. So that's the feature. That's the clever feature, that the intercept and the slope vary across individuals, because then you have this picture, the development across time here, for 3 individuals, individual I1, 2, and 3, they differ, those developments. Individual 3 starts very low relative to individual 1 and also grows at a lower rate than individual 1. What does that mean? Well, usually, intercept is where x is 0, so intercept sits here behind the podium, and therefore, intercept eta 0 does vary across I, It's eta 0, 1 is highest, eta 0, 2, second highest, eta 0, 3 is the lowest. And the growth rate, eta 1, 1 is the highest. Eta 1, 1 is higher than eta 1, 3, right? So we get intercept and slopes that are different for the different individuals. And that's the key feature of this modeling. So why don't we do that all the time in regression analysis? Well, we don't need to. We typically don't have this longitudinal repeated measurement setting, this hierarchical data setting of time points within individuals. But actually, econometricians often work with these kinds of random coefficients, and it has to do with heterogeneity matters. If you look through our user's guide, we have examples of random coefficients where you don't have longitudinal data nor multi-level data. There's an example in the user's guide for that, and it's a reference to the econometrics literature. Anyway, so those intercepts and slopes are now becoming not fixed effects anymore. Not fixed effects is what we work with in regular statistics, right? A parameter is fixed unless you get into Bayesian analysis. Parameter is fixed, but now the parameters are variables. So you have to think about these as variables. Eta 0 is a variable, eta 1 is another variable. They are not observed. They're not measured. They're latent variables, continuous latent variables. So a variable, it can have a mean, a variance, a whole distribution. It can be regressed on other variables. It can predict future variables. In any case, the typical thing here to do is to take these intercept and slope as dependent variables. Dependent variables. The term is slopes as outcomes for the regression coefficient, eta 1. And do another linear regression onto the observed variable w. Observed variable w. So you have an intercept here now called alpha 0 and a slope called gamma 0. Alpha, gamma, times the observed covariate w plus a residual, which you can hardly pronounce, but it's a Greek z or z, z sub 0 and z sub 1, residuals. So these are two linear regressions. So the example then could be y is head circumference, x is month of age of the child, w would then be mother's drinking during pregnancy. W would be mother's drinking during pregnancy. We will call that a time invariant covariate, as it says here. It does not change with time. It stays the same with time. But these are the two equations we work with. And in multi-level literature, like Radenbush and Brag's book, or Goldstein's book, or Snyder and Bosker's book, or Singer and Willett's book, this is going to be called a level 1 equation, and these are going to be called a level 2 equation. Level 1 and level 2. So if you then have a, what does this picture show? Well, and we now have to think about directions here and signs of relationships. If W increases, say that this is mother's drinking during pregnancy increases, the picture shows that eta 0 diminishes, decreases. So for a high mother's drinking, eta 0 is low. High mother's drinking, the head circumference at birth is low. So this is then a negative coefficient here, because it's a negative line, right? It's linear regression. Where does that sit in the formulas? Well, it's gamma sub 0, right? Gamma sub 0 is negative. So you scribble here, gamma sub 0, negative. Have these little filling in exercises to cure your jet lag. So we could surmise, we could hypothesize that it's going to be a negative relationship. And also, perhaps for the growth rate, is there perhaps a negative relationship? So that when mother's drinking is high during pregnancy, the child's head circumference grows at a lower rate. So that would mean that gamma 1 is also negative in this case. So that's looking at the formulas then. And then we repeat this on the right screen here. You may want to start, if you think about modeling, you may want to start with a picture like this. This is how I think, this is how the data looks from the screen. Looking through Mplus graphics output, data looks like this. And if you want to look at formulas to be able to read books and articles on this, we repeat the level 1 and level 2 equations. But now we're going to focus on going to a modeling picture. So all of the examples, 130 or so in the user's guide of Mplus, are explicated by a modeling picture like this and a few words, but can always be traced back to equations. So we take an example here of 4 time points. Time point 1, 2, 3, 4. It's one continuous output. Sorry, one continuous outcome, y, such as head circumference or math achievement. It's a univariate variable, right? But it's measured at 4 time points. So you have a data set with 4 variables. So think data set here. You have 4 columns, time 1, time 2, time 3, time 4. We're going to talk about data layout more in detail in a while. But it's time point 1, 2, 3, 4. And we're going to say that the outcomes y are a function of the random coefficients here, eta 0 and eta 1. And we have already agreed that they are unobserved variables. They're latent variables. Just like parameters are unobserved. But here it's parameters that vary. So they are not known, they're unobserved, and they vary. Therefore, they can be called latent variables. So this is the random intercept. This is the random slope. And we may call them now, as we're going to try to use these terms consistently throughout here, a growth factor, or an intercept growth factor, and an intercept slope factor. So we're going to talk about them as growth factors. And we're going to talk about this part of the model. You could put a nice little brace here that covers this much of the model. We're going to say that that corresponds to level 1, equation 1 here. This is equation 1. Whereas this part of the model corresponds to equation 2, A and B. You know, how the etas are explained, their variation is explained by W, is in equation 2A and 2B. So multi-level modeling can really be seen as level 1 and level 2 in this case. And we'll say this many times, so don't worry if you don't follow it right now. But you see, for those of you who have taken day 1, you will then see that this is the measurement part of a model, how the observed variables give information about the latent variables, or put another way, how the latent variables influence their indicators. It's called the measurement part of the model. So this is the measurement part of the model in SEM, structural equation modeling, factor analysis terms. Whereas this part, level 2, is the structural part of the model, describing variation or covariation in the latent variables. So in this case, the 2-level feature of multi-level modeling for longitudinal data turns into actually a single-level model. A single-level model, but where instead of having univariate outcome, we now have multivariate outcome. We have, you know, the same outcome at 4 time points can be seen as having a 4-variate outcome. And we're going to talk about this distinction between the single level multivariate approach and versus the univariate 2-level approach a little bit more in detail. But I just want to anticipate that in case anybody wonder, where did the levels go? Well, the levels just went into a multivariate vector instead. And we're also going to claim that that's the more powerful approach to doing growth modeling, this single-level multivariate approach. But in any case, back to the main story. So where are we? Well, here, if you start with level 2 for a change, you have then on these paths, these are linear regressions of etas on W. we're going to be less concerned with the variable type, observed versus latent, than what the scale is of the latent variables. In this case, the scales are continuous, right? So continuous dependent variable related to a predictor or a covariate is a linear regression. So this is a linear regression, and that's equation 2a and 2b. So if you were going to scribble something here for that path, what would you scribble? That's right, gamma sub 0, and here gamma sub 1. Those are the path coefficients, so to speak. They are the regression coefficients sitting there. And of course, alpha 0 sits here at the intercept, and alpha 1 sits there. And what are these little arrows? Well, they are the residual, z sub 0 sitting here, z sub 1 sitting here, and we allow them to covary, residual covariance here, which is represented by the double-headed arrow. That was the easy part. Now, what about this part? Well, that relates y to eta. And how does y and eta relate? Well, we only have one y there, you might say. No, we don't really have only one y. We actually have a t subscript, which was time. So we have 4 y's if we want to. Each of the 4 y's is influenced by eta 0 the same way, right? Each of the 4 y's is influenced by eta 0. So we have an influence from eta 0 to these y's, and it's actually then, the influence is a invisible 1 here. 1 times eta 0 is how we could write this. So these path coefficients here, 1, 2, 3, 4, are all 1. They're all 1. Whereas for eta 1, the influence of eta 1 on y is captured by x. Excuse me. X is the coefficient. X sub 1, x sub 2, x sub 3, and x sub 4. So the x values sit here as path coefficients. And we're going to talk about that in detail, and Linda's going to go through examples of it. But it's a funny situation here. It's sort of suddenly things get reversed. We start out by saying this is the h variable, this is the slope, multiplying that. Now we're changing it to this being the variable and this being the slope. So this is the variable, and the slope is x sub t here. And we're going to call the x's time scores. And we're going to relate time scores to, in this case, factor loadings. And later on, we're also going to cover cases where the time scores, the factor loadings, actually vary across people. Now, forgetting about those details now that we're just anticipating here and not going into details about yet, the way to look at this is then to say, wow, now the growth model looks like a confirmatory factor analysis model. You have 2 factors, and they have a very specific influence on the y's. For instance, all of the factor loadings on the first factor are 1. A very confirmatory in the sense that some parameters are fixed, in this case to 1. And we're also saying that we have a covariate that influences the factors. So it is actually a so-called mimic model in the SEM framework. Mimic being multiple indicators and multiple causes, in this case only one cause. And it's a very specific model saying that the influence of W on Y is mediated by these 2 growth factors. There is no direct influence from W to Y, is what this model says. That's typically not even thought about if you do standard multi-level modeling by standard multi-level modeling packages, that it implies this kind of no direct effect models. But what's interesting then is that this model fits the data surprisingly often reasonably well. It's the right kind of model for growth situations in very many cases. So typically, you don't have to modify it too tremendously much. The second aspect is that once you're in this modeling framework, this latent variable modeling framework, it's so easy to generalize to all kinds of settings. For instance, we know that mother's drinking may be misreported. What if you could take measurement error into account? You know, measurement error in a covariate or a predictor, so-called X variable, attenuates the relationship. So measurement error makes these slopes look smaller than they actually are. So you may want to have multiple indicators, multiple measures of mother's drinking. Actually, there were available in this data, repeated measures. So you can actually have a factor analytic measurement model where you can have a latent variable here with multiple indicators of drinking. It would be very easy to generalize this model to that setting. Likewise, on the dependent variable side, these could be latent variables. The head circumference example would not be relevant. But for instance, if you talk about, as we will do, aggressive behavior development in children across grades, you have typically a measurement instrument. Like Nika Alongo here has been using a so-called TOCA, teacher-rated aggressive disruptive behavior instrument, which has about 15 items in it. Sometimes you use the total score, but sometimes you may be interested in subdimensions of that score, and you don't want to sum up a small number of items because you get an unreliable score. So it may be better if you have multiple indicators of a latent variable at each of these 4 time points. And that kind of growth modeling is also possible to do. Not to mention that you could easily include direct effects. So for instance, mother's education may be more important for the child in 10th grade than in 7th and 8th grade. So there is not only an indirect mediated effect of mother's education on math achievement, but a direct effect. All kinds of generalizations which we're going to take a look at here. So that's an important slide, and we'll come back to it a couple of times during the days. And there's lots more to be said about it. One thing that often comes up and that we will emphasize here and there is that the words become a little bit complicated. We're going to talk about intercepts and slopes here, intercept and slope. But you have to then recognize, for instance, if you talk about this intercept, you want to try to explain the variation in the intercept by a covariate. So you want r squared in this equation to be high, right? And you are then interested in, well, how big is the variance of this, and what is the mean of this? And then you're going to come into terms like this intercept has an intercept, and it has a regression coefficient, and its mean is equal to, as in regular linear regression, the mean of this intercept is equal to the intercept plus the slope times the mean of the covariate. So we will have to rely on your linear regression knowledge. This dependent variable mean, the mean of this dependent variable is the intercept plus the slope times the mean, sample mean of that covariate. Sometimes people get confused that intercepts have intercepts too. But now you will not be confused. I hope. All right. So just a few more general words. You will be, in your career as a longitudinal modeler, which some of you are now embarking on, you will be exposed to many different teachings from books and from software literature and articles out there. And we try to summarize this a little bit and say that there are at least 3 different frameworks, or 4 different frameworks. In statistics, we talk about the so-called mixed linear model. Mixed implying that you have both fixed and random effects. And we're going to talk about the random effects of what we have talked about. You know, it's, in this case, growth factors that vary across individuals. What's a fixed effect? Just quickly. Well, it's a growth factor that has 0 variance. So it only has a mean. The growth factor, a random effect, that is, with 0 variance, is a fixed effect. So it's just a special case of a random effect. So when Sasproc Mixed talked about mixed models, it means a combination of random and fixed effects. But it's pretty much the same thing as we've talked about, pretty much meaning that this ellipse is overlapped by several other ellipses. One ellipse, or circle I guess it is in this case, one circle is the multilevel circle. Multilevel modeling seems to have come out of educational methodologists' work. Primarily, I put in Raudenbusch and Braich's work there, identified by their software, HLM, Hierarchical Linear Modeling. Smart job there to call the program the same thing as the modeling activity. Somebody should have called our program SEM. Well, you still have a chance. So that's almost exactly the same as a mixed linear model, and also in software capabilities. So these two circles are very close. Their differences are not even interesting, I think. Then you have the SEM, Structural Equation Modeling Circle. And it cannot do everything that the two other circles can do. You know, up here is what SEM cannot do that these guys can do. For instance, SEM, the standard conventional SEM framework, which is a mean and covariance matrix analysis framework, cannot handle random slopes. Cannot handle random slopes. I'm just saying that in a general, vague fashion now, and I'll be more specific in a second. So SEM doesn't go far enough for all the kinds of modelings that we're interested in. On the other hand, SEM can do certain things that these models cannot do. Now, the box I put here is, again, the Mplus box. And we try to make a distinction between latent variable modeling in general and SEM specifically. We see latent variable modeling as a more general activity than SEM. And actually, some people call Mplus an SEM program, and we're a little bit miffed by that, because Mplus is much more general than what the SEM programs do. It's an item response theory program. It's a latent class program. It's a latent transition program. It's a survival analysis program. It's a complex survey data analysis program, etc. So we have then a more general approach in Mplus. So you see the box here covering everything that SEM does and most of what these frameworks do. But there is still a little bit of slippage up here that we haven't covered yet. For instance, crossed random effects, or multi-level models with many levels are not yet covered in Mplus. But as you see, the arrows show that the box keeps getting pushed up here for every new version. So we hope to get up and encapsulate those. So that gives you a flavor of the differences in a general fashion. Now, specifically then, here's a summary of some details. In the pages that follow after slide 26, you have the statistical formulas for what's said here. This is, after Linda heard me talk about the statistics for a couple of times, she said, let me just summarize that in words, okay? So here it is clarified. Comparison between these three frameworks. Essentially, multi-level and mixed linear models are the same. SEM differs from the multi-level mixed linear models in two ways. Treatment of time scores, you know, the X variables that we used, the term X that we used. Time scores are data for multi-level and mixed linear models. It's data, whereas in SEM, time scores are parameters. We call the time scores factor loadings, right? And you may want to note here that here, when there are parameters, we had X sub t, X subscript t, whereas here, when time scores are data, you can allow X to have subscript ti. So individuals can have different times of measurement in this case. So the typical example would be you go to the hospital for being treated for something, and they ask you to come back in 4 weeks or a month. And some people come back in 4 weeks, after 4 weeks, for the second for the first follow-up measure, but some other people come back after 6 weeks. So the second time point, x sub 2, its value can vary from 4 to 5 to 6 across individuals, right? So that happens in many data sets, not in the data sets we talked about so far. So in these worlds, time scores are data, whereas in SEM they're parameters. So the advantage of this is that you can handle these individually varying times of observations. But the advantage of this is that you can actually estimate the parameters. So we don't have to fix them as 1, 2, 3, for instance. We can actually estimate time score parameters, as we will show you, giving a very flexible model, a model which shows, say, accelerated growth or decelerated growth across time. So there are pros and cons, and that's why Mplus allows you to have both. Either one of these is possible. If you want to scribble something Mplus-like here, you put at. That little keyword is key for using this approach. And we're going to talk about that. Now, the second difference is more subtle still, perhaps, treatment of time-varying covariates. We talked about time-invariant covariates. Time-varying covariates is covariates that vary not only across individuals, but across time. So in the LSAY math achievement example, mother's education and home resources would be time-invariant covariates. What would be time-varying covariates? Well, for instance, math course taking, which varies across the grades. How many math courses they take in the different grades could be a time-varying covariance. And in the multilevel mixed linear model world, time-varying covariates can have random slopes as well. That is, coefficients vary across individuals. So a given amount of math course taking may have different impact on the achievement for different students. Say students who are at a low level or a high level may benefit differently from a given amount of the time-varying covariates. So the slopes vary across individuals. So that is, apart from the growth factors, you have other random effects. Now, in the SEM world, time-varying covariates have fixed effect coefficients. You cannot let them vary across individuals. They can vary across time, but not across individuals. If you allow them to vary across individuals, you'll have a random coefficient times a random covariate. Product of two random variables, even if both are normal, will not give you a normal result. You fall outside of the standard covariance structure, mean and covariance structure, SEM framework. So these two limitations of the SEM is what are the key reasons why for this space up here, and has been the old reason for why, say, Steve Raudenbush wrote a critique somewhere of, who's an HLM person, of SEM not being sufficient for growth modeling, but he meant conventional SEM. He did not mean latent variable modeling in general. So there you have it, a sort of details of those differences. Now, here are the statistical aspects of that, and I'm going to skip over that. In general, our strategy during these days is to give you, on paper, much more material than we will cover. And that's intentional. We want you to go home with a lot of material, but we're going to sample topics from those pages, not try to rush through everything, which will have very little impact, but instead go through these selected pages in a more careful way. Here is a page that we're going to talk about again tomorrow. But I just want to give you a heads up on this. What we have talked about so far is the approach up here. This is how we're going to deal with growth modeling today. It's been termed the wide approach. Wide meaning that even though you have math achievement score, a univariate variable, you will have multivariate wide data because you have several time points. So you can think of this as column 1 up to column T in your data sets. So the time points are arranged as columns, as opposed to the long approach, where for person 1 you have the first time point, and below that on the next row the second time point, and then below that the third time point. That's the long approach. So wide versus long. So wide is a multivariate single level approach, which is what we talked about now. Long is probably the more common approach in multi-level programs. It takes a univariate approach. It will become a two-level approach. What are the levels? Well, level 1 is variation across time. Level 2, variation across individuals. Variation across time, variation across individuals. So the model really it looks like this. It's outcome regressed on time with a random intercept and a random slope on time. So this is like eta 0, which we call I for intercept, and this is eta 1, S. So there's only one Y, regressed on time, with random coefficients. And those random coefficients, as we will talk about in detail tomorrow, those random coefficients are latent variables, as we talked about, and therefore, on this level 2, which we also call between, they become continuous variables, continuous latent variables, circles. So you have the latent variable representation here on the second level, on the between level. Now, why would you want to do one or the other? Well, I think this approach, the wide approach, is more powerful when you can do it. And you can do it as long as you don't have extremely large number of time points. If you have 100 time points, this would be a 100-dimensional vector, right? And many have data like that. You know, you beep somebody and ask them, are you smoking or something like that. And you can get very long data sets that way. So this may not be practical. But if you don't have too long data series, this, as we will show, allows for more modeling flexibility. More modeling flexibility. But when you have very long time series, you may want to take this long univariate approach, because then it doesn't matter that you have 100 time points. You still have only one Y. 100 time points means that you have 100 members of the cluster. And what is a cluster? Person, right? Cluster equals ID. So you have a cluster, which is the person, and within person, you have cluster members, that is correlated observations across time. So, and multi-level modeling has no problem with having large cluster sizes or varying cluster sizes. You know, some people have only 50 time points measured, some have 100. That's no problem in that approach. But when you go to the univariate approach, you give up on some modeling flexibility that we're going to talk about. You give up on some modeling flexibility, and we're going to mainly stay with this approach. I'm just saying that because this approach, the long approach, is usually what you see in mixed linear, SAS-proc mixed and multi-level HLM, although those approaches also have, those softwares also allow a multivariate feature, but not for all models. Whereas in the SEM approach, you typically only see the multivariate approach so far, whereas we try to go back and forth between the two approaches depending on the situation. Just so you know, the general layout. I'm going to skip this page, but I'm going to mention what you have on slide 35. We're going to spend the whole day on growth modeling using this third alternative. You know, I had 3 different versions. The third was the random coefficient regression, which is the model we talked about on the previous slide. But note that this growth curve model, as we call it, this is the model we talked about, alternative 3, is not the only model that you may want to use for longitudinal data. And in fact, on day 3, that is day 5A, let's say on Wednesday, that is day 5, no, sorry, Wednesday, day 5B, you're going to also be acquainted with an autoregressive model for longitudinal data. On day 5B, it's going to be called latent transition analysis. Latent transition analysis. And it's an example of an autoregressive model, which is an alternative to the growth curve model. So you have to be familiar with those two basic modeling choices. Which one fits your substantive application the best is the question. So here we're saying that we have a learning process. Studying makes you do better and better across time. Your test score at time 2, at grade 8, is not influenced by your test score at time 1 in grade 7, but rather it's influenced by your learning process. So how you scored on the test here does not influence that. There's no arrow here, whereas here you have an arrow directly here. So an example here may be how much you smoked influences directly how much you smoke the next time. A direct dependency between the observed variables. So you have to ask yourself, what's a growth process here? What's most reasonable? I would think that this probably is better for achievement development and head circumference development in terms of those examples we talked about. But there are many examples where this is probably better. Although you could imagine hybrid situations where how you perform in grade 8 is influenced by what you learned, but perhaps also by how you did in grade 7. The test score itself, because if you did well, maybe you're less nervous and feel more comfortable with the testing situation. So not only do you draw on your knowledge, which is sitting here, but you draw on how well you did or how poorly you did at the previous time point. So you can imagine hybrid models, and Ken Boland and Pat Kern have been interested in those models, and so has Jack McArdle and Hamagami. And you have some references in the back. In the back, you have a lot of references, and you may want to study up on those. Boland and Kern have a new growth model book out by Wiley, and that's also in the references, which takes this latent growth approach, similar to what we're going to talk about, although more geared towards SEM. So just be aware that you shouldn't always jump into this toolbox. Sometimes this one is better. We're not going to talk about this one with continuous outcomes, but we are going to talk about it with in the categorical setting on Wednesday. Now, we like to be in this latent variable framework, that bigger box. We think of that as a bigger box. For the following reasons, and we're going to go through all of these reasons with examples today. We talked about being in a latent variable framework gives you a flexible curve shape. Why? Well, this is because those x sub t time scores can be parameters that you can estimate. And we will see that the time scores estimated gives you a flexible growth curve shape. So that you may want to write here, x sub t is a parameter that can be estimated. X sub t is a parameter that can be estimated. But you can also, in this latent variable modeling framework, allow for individually varying times of observations. And to the right, you write x sub ti read as or handled as data. X sub ti handled as data. So this is the multi-level mixed approach. And this is the SEM latent variable modeling approach. Both of those approaches are incorporated in the general latent variable framework of Mplus. Now, why we like to be in that framework is that you can do regressions among random effects. You can say that growth rate is influenced by the starting point, the intercept, the initial status. We're going to talk about examples of that. We can easily work with multiple processes. We talked about achievement and attitudes. You can easily work with modeling of zeros, which is important for many behavioral researchers, where you have a very skewed variable with a high piling up at the lowest point as a floor effect. So at a certain time point, there's a large portion of your sample that has not yet experienced the activity, has not yet engaged in a kind of activity such as heavy drinking, for instance. We're going to talk about modeling of zeros, which is very easily done in the latent variable framework. Multiple populations, be it gender populations or different cohorts or treatment and controls. Multiple indicators of latent variables. I mentioned TOCA instrument as one example. We're going to go through that in detail. Embedded growth models, which is when the growth model is really only a small part or only a part of a bigger modeling effort that you're interested in. I'm going to show examples of that. And the final reason we like and the number one reason we like this is a list of 10, right? 1, 2, 3, 4, 5. We like latent variable modeling. The perspective of that for growth modeling is that you can work with categorical latent variables, not only continuous random effect, but categorical latent variables, so-called growth mixtures, where the mixtures, the categorical latent variables, can represent qualitatively different types of development. So you have individual differences in development of two types, continuous variations, but also categorical, qualitatively different types of growth curves. We're not going to talk much about that. That's really day 4. But day 4 reappears in its multi-level version during day 5A. So Linda's going to go through an interesting example tomorrow on multi-level growth mixture modeling of the LSAY data, which will actually then summarize a lot of the things that we talk about tomorrow. So those are our reasons for going forward in this framework. And we'll go through all of these, most of these bullets, except the last one, during today. And with that, I think I will stop talking for a while.
According to our schedule, we should take questions, don't you think?
Yeah. Good.
And have a break, because then I can start after the break. Okay.
So the schedule says that we should now allow a question and answer session, and then you have disturbed your first morning coffee, which we welcome news to the long-distance travelers here.
Yes.
At least. So let's hear. Who has the first question on the generalities that we talked about this morning? And again, this is, just a start, so it's the generalities will soon give way to specifics. Yes?
Before, I was curious, is this sort of equivalent then to a population average generalized estimating equation, how you were describing the univariate versus the way HLM does it?
I think, so the question was about population average versus individual specific. I think you would see both of them as individual specific type of modeling.
Okay.
So they're one and the same, actually.
Okay.
By the way, when you post your questions, and you may try to remember that for the next block at least, write down on the slide that you have a question, so you can just point to the slide now in this here. So who has an interesting slide to point to? Yeah, they weren't very interesting, were they? An uninteresting slide, yes.
I have a question, a general question. Will you cover the recurrent event data analysis?
Recurrent event? Could you elaborate on what you have in mind?
Smoking, like how many, for example, adverse event. Particular adverse event, how frequently it is occurring in a certain number of months. The particular event is occurring.
I don't think I understand the setting. Could you just give a little bit more detail of the example? So you're asking a person how much they smoke?
No, just not smoke. Let's say clinical trial, like a safety data analysis, for example. We are interested in particular event. It is occurring in subject. It is occurring for particular subject within 1 week, another subject after 2 weeks.
Oh, okay. Are you talking about survival analysis?
Yeah. Not survival. Survival is time to first event, but
Time to first event. Yeah, but generalizations of survival, you can have recurrent events is what you're talking about. Yeah, no, that will not be part of today. We won't have time to get into any survival analysis.
does the Mplus cover this methodology?
Yes, it does. And actually, Mplus covers not only the discrete time, but also the continuous time survival analysis. And if you're interested in survival analysis, from the Mplus point of view, a former student of mine, Catherine Mason, wrote her dissertation on that topic, and her dissertation is posted on the Mplus website. And furthermore, our statistical colleague, Tihomir Asparoho, has written a paper with me on survival analysis in Mplus, and it's a paper, it's a JSM, Joint Statistical Meeting Proceeding paper sitting on our website as well. Other questions? Yes, lady there in the middle.
Can class deal with population weights?
With what did you say?
Population weights.
Population weights. You mean sampling weights?
Yes.
So you're asking whether Mplus can take that into account? Yes. Mplus has several complex survey features now. We have weighting, sample weights, both at the within and the between level that we can do now, and also stratification and clustering. So we have quite a few features for complex survey data at this time.
We're actually going to talk about that tomorrow morning. I'm pointing to the website. There's actually an SPIR project within Mplus that focuses on that topic. And there's a whole section on the website with papers on complex survey data analysis. So actually, Mplus is quite well developed for that kind of analysis, and usually well developed, thanks to that project. Yeah.
On slide 26, when you mentioned that the SEM approach allows you to estimate time scores and that provides more flexibility, I was just wondering if that means that when you're in a multi-level approach, you're limited to the occasions of measurement that you've specifically collected. I don't know, it's just maybe if you could elaborate on what you mean by flexibility and why estimating time scores is more flexible than having the specific times of measurement that you provided. You know what I mean?
Actually, we'll be doing an example after the break of that, but basically what we're saying is you might estimate a linear model, and your time scores are going to be, as we're going to see after break, 0, 1, 2, 3, let's say. But let's say that model really doesn't fit the data well, and you can see that perhaps you want to free one of those time scores and estimate it rather than holding it at a value. Well, then you can free it and estimate it. So that's what we mean by that.
I have a second question.
Well, let's spread the opportunities. Yes, in the back.
Yes, I was wondering if Mplus allows you to figure out a way to, for example, to figure out the variance explained on that intercept or slope that you're predicting at level 2.
So for the dependent variables, the intercept and slope growth factors?
Yes.
Yes, you can get an R-square value for that.
Okay.
Right.
Is that what you're asking?
Yes.
Okay.
Which is very useful to look at, and as we will see, the growth slopes will be the hard ones to try to get high R-square score.
And just one more thing, and that's the standardized option of the output command, just so you know where to do it.
Yeah. Colorado.
Yeah, this is a little new for me, but I had a question. I'm interested in coping processes across time. And so if I'm looking at the slope of the time variant across time, I'm very interested in linear versus nonlinear trajections. And would you be able to see that? Would it differentiate, for example, subpopulations in a sense of people who are coping more linearly and then those that are shifting into a nonlinear process that might be considered more pathological or whatever?
Sounds interesting.
Well, doesn't that sound like Resnick model?
Yeah.
Right, which will, I think that's actually 5B.
I need day one first.
This gentleman is doing day 1, but he's already asking relevant questions for day 5A afternoon, I think it is.
We'll see who's right.
So, no, that's exactly a good example of the last bullets that I showed, advantages of latent variable modeling. So you have qualitatively different kinds of development. Latent subgroups of individuals with different trajectory shapes.
Okay.
So that would be growth mixture modeling. And so last March we talked about that. That's the day 4 topic, which now in a multi-level setting is covered in day 5A. So do come back.
Yeah, no problem.
Okay, any more questions? Back there?
My question is about the slide number 15. And, yes, it shows a graph of data by grade. My question is whether it is the same exam that's being administered to students in grade 7 as they progress through grade 7 through 12.
Yeah, that's a good question. So is it the same test at the different grades? Which is actually a topic that we will touch on when we talk about multiple indicators. It isn't the same, but through the magic of so-called IRT, item response theory, the test scores are comparable in the same metric across time. It's interesting how they did it. You know, everybody got a test here of 60 dichotomous test items, right, wrong answers, I think. And those who did well in grade 7 were penalized by given a harder test in grade 8. But not all items were different. Some items, anchor items, were held the same. So you can equate the measurement parameters of those and keep things on the same scale. And then they went forward in that way. That's the adaptive testing aspect of this. And although that's commonplace in educational achievement testing, I think it should be used much more in other areas too, like child development, where you can have a slowly developing measurement instrument that becomes age relevant. And we'll try to cover that a little bit within the multiple indicator topic this afternoon. There was a question over here somewhere.
Yeah, actually, I asking a similar question. So that scale need to be on one common scale, like vertical scale, then you can compare the scale score. But what if we have separate scale within each grade? So it's not, because it's a standardized, it's a performance test. So it's compared with your performance label to show growth, but not each scale is separate. Can that still use in this?
No. So the Achilles heel of growth modeling is that you have to have the same score in the same metric at all time points. It's very critical. You cannot study change of individuals over time if you also change the measurement. Then you can't separate it out. And actually, there's a good article by a former colleague of mine, Seltzer from UCLA, who talks about exactly that problem of using scores that have been normed within grades or standardized within grades. His name is S-E-L-T-Z-E-R. You can Google him, Michael, and he's done a nice paper on the difficulties of that. Now, but the key is that if your measurement instrument needs to be changed across time, change it in a design fashion, holding some parts of the test equal between adjacent time points to be able to put things in the same metric. And we're going to talk about that in multiple indicators. Yes?
How many data points over time do you need for growth modeling? 2, at least 2?
Well, we'll do that after the break. Is that okay?
But generally speaking, you can do some simple things with 2. You really want 3 to even be serious, and you really should have 4 or more. To answer you quickly.
So we'll tell you why after the break.
Yes.
So quick question, still on slide 33.
33?
Yes, I think you mentioned that the wide method is more powerful than the long method. And Linda said we are going to use examples to illustrate the advantages. I'm just wondering, those two models, they look very like analogous to each other to me. And I wonder, for the same model, am I going to get the exact same estimates from both models?
Great question. Thank you. Very pedagogical. We talked about this before, right? Exactly the same results. To get exactly the same, if you have a model here, it can be represented this way, with certain, restrictions. So let me take an example. For instance, if you have this model, you see that you have one residual here. You have one residual variance. If you want to replicate that model in this setting, you have to set the residual variances equal across time up here. But if you do, you're going to get numerically exactly the same results. So if you don't, then you've done it wrong. So yes. But the key is that you can do more in this range.
So we can relax that constraint.
Exactly. Yeah, and we will do so throughout the day. Thanks. Very relaxed by then.
You may have said this. I was wondering if SE or Mplus requires an equal number of occasions for each individual measurement occasions.
Equal number of measurement occasions. No, so that's so Mplus does not have to have the same number of occasions measured for individuals. So if you have a maximum of, say, 10 time points, you can see in the multivariate approach, you will see then that as some people having missing data, say dropping out. So that becomes a missing data issue. And that's taken care of very thoroughly in Mplus, that is missing data is by the standard approach, just for those of you who know about missing data, is the MAR in Little and Rubin terms. But there are also several non-ignorable missingness modeling opportunities, pattern mixture or missingness as a function of unobserved variables. All of that's very difficult to do, but it is there.
Is it possible for multi-level analysis where you have a cluster area that is missing data? Can Mplus handle that?
So a cluster variable that's missing data?
Suppose you have census tracts, and you have some census tract information on some tracts, but some are missing on some tracts.
Do you, but you know which cluster they're in, but you just don't have data on those? So it's, so that's missing data on the highest level, yes. On level 2, for instance. I thought you meant you have missing data on the cluster variable itself.
No.